we saw that to get the area under a curve, we could multiply the width of each little rectangle times the height. And if we took the limit as n approaches infinity of all of the rectangles, right, getting infinitely small rectangles, that would give us the actual area. So when we did that, we multiplied two things together. It was the length, which was our delta x, and then our function f of x. But to do that, we had to sum them. And so we needed to use a sum, and the sum was of the function x. Now, we evaluated these using really I. Okay, I would be like the first one, the second one, the third one, and each one times delta x. And so I here goes from 1 all the way to n. Okay, this is what we used to get the area. Okay, we took the limit as it approaches infinity of the summation, okay, right, of a bunch of different lengths times widths, okay? Or really, it's really more like base times height, okay? Now, this summation notation is useful for Riemann sums, and let's go over just a little bit about summation notation. So, what does this mean? What if we take, like, let's just do a classic one, I, say from I equals 1 to n. Okay, this is shorthand notation for the following. 1 plus 2 plus 3 plus dot 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 plus n. Okay? That is the sum of the first n terms. Notice not an infinite sum, right? It stops at n, but the point is n could be any number. Now, this is very different than sort of taking an infinite sum. If you had an infinite number of numbers together, you simply get infinity, right? The limit as it approaches infinity is of really when we did it, it's of a finite area, okay? Now this has an actual equation, meaning, what is the answer? And you could look at it, well, the 1 is just 1, but if you take the first two, 1 plus 2 is 3, but if you take the first three terms, 1 plus 2 plus 3 is 6, you can think, well, how can you get the first three terms and get 6 out of it? In the same way that it'll work for all of them, it's simply this term times the next one divided by 2. So this is equal to n times n plus 1 divided by 2. Okay? What are some other sums that might be useful? Okay, consider the following. What if we have something like this? Okay, so we've got a sum, and we go from I equals 1 to n of 3. What the heck? There's no I in there, so what would you do? Well, each time you would add 3. Now the last one, it's not n, right? Because it's like you're changing I. This one doesn't change, it's always 3. And so this would just be 3 times. How many 3's do we have? We have n of them. So this would be 3 times n, right? You could put a in there, it's a times n. Okay, it's a nice one. So speaking of that, what if we do have a constant? What if it's the following? What if it is 3 times c? For I equals 1 to n. What do we do here? Well, what's interesting is if you have, in this case, you're going to have a 3n to c for each one. But note that you could actually, if c is a constant, you can pull it out. And so you could say, well, you can pull the c out of this. Sorry, sometimes summations, we only get so much practice writing our sigmas, capital S for sum. And you can pull it out because it is a constant. right? And we already saw that's 3n, so it's 3nc. Okay, so this is just a little bit of summation notation. It's important to get used to it because you are going to see it. And the in piece, like the top could be anything. It could be a number. Like let's just do another example. What if we had the following? What if we were looking at the sums of x squareds, x equals 1, 2, 3. What is this going to be? Well, you first put in a 1 squared plus 2 squared, and you stop when you get to 3 squared. Okay, now we did have a formula for all of the squares, but this one we don't need it. We can just write it out. 1 plus 4 is 5, plus 9 is 9 plus 5 is 14. Okay, so just a little bit on summation notation. Now, let's also consider an example here. We're going to do another Riemann sum. What we're going to try to do is the following. Okay, I'm laughing because I know it's coming, but sorry, I shouldn't do that. Let's find, I'm just going to call it this, find Riemann sum. So this is going to be an example. So we're going to find the Riemann sum. Riemann, amazing mathematician who came up with this Riemann sums, obviously. So find the Riemann sum of, we're going to do x cubed minus 3x from our interval will be from 0 to 3. Okay? We're just going to do 0 to 2. Let's do 0 to 2. Okay, so if you want, you can interpret this as the area under this curve from this point to this point. And we're going to use this formula. Okay, so let's see now how we can apply this formula to figure this out. Okay, so start just by writing it out. Okay, so you've got the limit as n approaches infinity of the sum. Now you've always got this I equals 1 to n. Now what's f of xi? Well, you've got to put an xi into this, right? So it's xi cubed, right? Minus 3xi. Now note that I is a subscript here, okay? It's not really, it's like a variable. It's not, x sub I, why is this used? You'll see this a lot in calculus. It's because they're trying to distinguish between I and n, and so you typically are summing i's. Just think of it as like another variable. But then this is times, okay, so here's our function, times delta x, which we recall is b minus a over n, so this is 2 over n. So we need to get the correct variables here. We don't actually want the x's. And so the way to properly do this is to write out the partition. Okay, and so what's the partition? I mean, in effect, you're starting at 0, and then you're adding like 2n each time, because that's our delta x. So then you get 2 over n. And you would add, you keep adding 2 over n. So you would get 4 over n, and then 6 over n, dot, dot, dot. In the middle, okay, what you actually end up with is 2i over n, okay? Right? Because when I is 1, you get this one, 2, this one, 3, this one. And it goes all the way into the last one, which is going to be, in this case, it's basically, it's going to be 2, so it's 2n over n. Okay, so when you write the partition, now it allows you to properly plug in. And what you do is you plug in the arbitrary one, which is simply this 2i over n, okay? Because we're generalizing it. So what we're going to do, we come back to this when we plug in 2i over n for our x's. So we got the limit as n approaches infinity of the sum from I equals 1 to n. You don't start with the n, you conclude with the n. Okay, fix this. And then we're just going to copy everything else down, but we're changing, trying to go too smudgy. I equals 1 to n. And so instead of xi cubed, we're going to do 2i over n cubed minus 3 times 2i over n, and then we leave the 2n. That's what you want. You want everything in terms of i's and n's. Now, the next step's a little bit interesting. So when you're doing the sums, okay, you're actually summing i's, right? Like here, or it's a bunch of i's. You're not actually summing the n's. The n's are what you end up with. So what we can do is we can pull some things out of here, okay? Additionally, there's a property that I didn't write here, but it should make sense. And I can probably fit it in here. And so what's the property that, property I would like to write? It's the following. I can probably squeeze it in here. Well, we'll do it at the top. So the sum of f plus g is basically equal to the sum of f plus the sum of g. Okay? Do you see why that's true? Okay. Hopefully it's clear, because you're just summing a bunch of things. And so clearly if you sum all the f's and the g's, you can rearrange the order and do all the s first and all the g's second. And so here we apply this sum separately to the two terms. The 2n goes to both of them. So the 2n can come out front, okay? So we've got the limit as n approaches infinity. That stays. Now this 2n can come out front of the whole thing. And I've got now two separate sums. And my sums are, what? Well, I've got 8i cubed over n cubed. Just multiply it out. And I've got a separate sum and that separate sum is going to be 6i over n. Now certainly the I equals on to n should stay there, and we're getting close, okay? So now, the sums are, I'll just write it in for I equals 1 to n, I equals 1 to n, and now we get the result of the i's. Okay, for this individual sum, we can pull out the 8n cubed. Okay, let's go ahead and write it out again. So if we pull out the 8n cubed, we get 16 into the fourth, and now we're just left with the I cubed. And then here, now I multiplied out by the n, so we'll do that with the 6 too. I get 12 over n squared. And then you're just left with the I. So this is kind of what you want to do on these. You want to basically get these modified so that you're only left with the I terms. Now we have this sum. It's just n times n plus 1 over 2. That's the goal, is to transform it to an n. Okay, but what about this one? Okay, this one is a formula. Again, if you don't know it, you can look it up, okay, in your text. You don't have it on the right page. Let's see if I can get it right. I think it is the following. So the 16 into the fourth stays, and then this is going to be n times n plus 1 all over 2 squared. And note that this is very similar to the other one, which is just n times n plus 1 over 2. Finally, we have this setup to take an actual limit. Okay, Now let's see what we get. What we're interested in are simply the highest powers, okay? So the highest power of the first one is going to be what? It's going to be 16 squared, so 16 into the fourth over 2 into the fourth. And that is going to be 8, okay? You guys see how that works? By the way, this should be a minus. I think I changed it to a plus. Okay, so let's fix that. Just totally changed it here. Don't change your minuses to a plus unless you have a reason to. So these should all be minuses. Okay, and the limit obviously applies to the whole thing. So again, we've got 16 into the fourth over 2 into the fourth plus, who cares what else on the top. That simply, as n goes to infinity, we take our leading coefficient, it's going to be 8. And then what is this? This is going to be 12n squared over 2n squared, and so we get a minus 6. Oh, I realized I did something wrong. The 2 squared is a 4. Okay, so you got to square the 2 there. It's not 16 into the fourth over 2, it's 16 into the fourth over 4 into the fourth, and that is 4. And we get negative 2. What? Okay, we said this is how you get the area using this formula, and we just got something that's negative. So what the heck is going on? Okay, let's see if we can sort of try to figure it out. Okay, what's going on? Let's graph this. The graph is going to be something like the following. So it's from 0 to 2. At 0, you get 0. At 2, you get 2. So what happens in the middle? Okay, we can actually use calculus for this. So if we do like the derivative, we get, put it up here, f prime equals 3x squared minus 3. That's going to be factor of the 3, x squared minus 1, x is plus or minus 1. Okay, this means minimum and maximum. So the negative 1, if you plug in a negative 1, you get negative 1 plus, wait. No, I want to plug in positive 1, yeah. Positive 1 is clearly negative 2. So that's your minimum. And you get something that looks roughly like that. So how do we interpret this? The way we interpret it is the following. This part is actually negative. If you go under the curve, it's negative, and this other part, it should go more, it's not vertical, there should be some space here, is actually plus. Okay? Let me draw it again so it makes more sense to you. This is a critical piece. Okay, so what we ended up with is a curve that looks like this. This part's negative, and then that part's positive. Okay? Yes, that's the way it's done. So it is not the area that we're actually figuring out. It's something close, and the area is an interpretation that we will fully flesh out. What we are computing is called an integral. Okay? This is the integral of this function. Okay? And the way that you write the integral of a function is the following. Okay? This is our function here. So the integral of x cubed minus 3x from, we went from 0 to 2. Now this is very close to being exact, okay? We need something else to make it exact, and I'll add it on at the end. But what it equals is the limit, which is what we did, as n approaches infinity, of the summation from I to n, did it again, from I going from 1 to n, of f of xi, it's up there. Delta x, where, you know, delta x is, as we've shown, the delta x equals b minus a over n. And what is this xi? I mean, really, it's like what you're doing is you're taking the first point, right, a, because it doesn't have to be 0, it could be something else. And then you're adding like a little bit more. And how much are you adding? Well, right, you're adding, like, to get 2 over, you're adding like 2i over n. It's sort of like this delta x. So it's sort of like I, delta x is the 2 over, so it's really I delta x. Right, because to get the second one, you're adding two delta x's, for instance. Okay. Now I said this was almost the definition. What's missing? Okay. This is the function. Okay, the function is here. But what about the delta x? The delta x is not like how does that fit in? Because b minus a over n uses the endpoints, but here you're multiplying two things together. It is a base times a height. And when we do this limit as n goes to infinity, your base becomes infinitely small, right? So if this is the height, the function itself, and the base is infinitely small, right? Instead of it being delta x, which is a finite distance typically, it is an infinitesimal differential, and you write dx. And the dx applies to our whole function. So that is what we just did, is we computed the integral, okay? Now, there's a lot to unpack here, and more is coming. But I will tell you this. Computing integrals is actually not about doing limits. Just like with derivatives, it's a big part, but when you compute derivatives, you're not computing limits, you learn the shortcuts. So you will learn the shortcuts for what's called integration. Additionally, you will learn precisely how to get the areas under curves as an application. With this piece, you can see all you need to do is find that middle point, and then you take the absolute value to make them both positive. But when you compute it, it's not really the area, it is the integral, and we're starting this out by doing Riemann sums.